Hello again, and we are back in Chapter 3. We're working on Lesson 4 today. Chances are we've gone through this in class already, so this will be some review for you. So it starts off with a money challenge, in which, yes, there's definitely money to be made. Looking for 2 volunteers with good powers of logic. Not everybody can be up here, but you may all have a chance to earn a prize if the 2 volunteers don't come through. So here is our money logic challenge. I've got 3 envelopes. The 2 students and I each receive an envelope. 2 of the envelopes have a $1 bill in them. The 3rd envelope has a $5 bill in it. If one of the students receiving an envelope can tell what is in all 3 of the envelopes, in other words, mine and the other student, and then logically explain why they believe that, they get to keep what's in their envelope. If neither student is able to do that, the rest of the class will have a chance. Now, some of you may think, oh, well, Prof would never give away a $5 bill. Well, that's not good logic, though. It's probably right, but it's not good logic. You need to think this one through and see if you can figure it out. So maybe pause this a little bit and think about it. If you're back, maybe you came up with something, maybe you remember what was in class so you didn't have to pause. But here's my thinking today. It's the point of this lesson. We're talking about indirect proof. In the last lesson, we talked about direct proof. Now this is proving something indirectly. And before we explain exactly what that is, we're going to solve this one indirectly, and it may give you a pretty good feel for what it means. So person A, one of the students, they have a $1 bill, not the 5. So person A indirectly reasons that Prof has the $5 bill, and here's how he figures that out. It's not just that Prof wouldn't give away the 5. There's a better flow of logic here. So here's the theorem he's trying to prove. Prof has the $5 bill. Interesting how he starts. He says, let's suppose that Prof does not have the $5 bill. Okay. If Prof doesn't have the $5 bill and he knows he doesn't have the $5 bill, then person B must have the $5 bill. Because I know I don't. This is person A talking. But if person B had the $5 bill, then he would right away know that Prof and I have the $1 bills. This is a contradiction, since person B doesn't seem to know what Prof and I have, unless person B is just not very smart. But since he doesn't know what Prof and I have, therefore what I supposed that Prof doesn't have the $5 bill, this one right up here, we suppose that Prof doesn't have it. What I supposed is false, and Prof must have the $5 bill. That's an indirect approach to proving something. And maybe you can see how that works. If you're trying to prove one thing, you suppose the opposite of that. You run into a contradiction, and it ends, therefore what I supposed is false, and then whatever you're trying to prove has to be true. This comes up in a book, Anno's Hat Tricks. And there are 3 of them, and we've done them in class. What I encourage, what must happen is all the comments and answers have to be conditional statements or some other type of logic. There are 3 such tricks. And again, we will have done these in class, and they all represent the idea of indirect proof. So let's look at indirect proof here. we're going to compare it to direct proof. Both of them are totally legitimate ways of proving a theorem. We use direct proofs a lot more than indirect, but they're both perfectly legit. They both use conditional statements. If this, then that. If this, then that. They both use logic, deductive reasoning. Sorry, a little too fast. They both use logic, deductive reasoning, and syllogism. So that's similar. Here's some differences. One uses logic to arrive at a conclusion to what you're trying to prove. Think back to that maze that we did last lesson. One first assumes the opposite of what you're trying to prove, and then uses logic and arrives at a contradiction. That's an indirect proof. A little confusing, but let's try this with a maze. I wonder how many of you quote-unquote cheat on mazes. If we start at A, do you instead go up to the ending up there and work your way backwards to get to A? I don't know if that's cheating. It's probably just smart. Well, here's our theorem. Maybe you've figured this out already in your head. Looks like we got to go left, huh? Not straight. So our theorem is, if you turn left at A, then you will complete the maze. So we're going to prove this theorem directly, using a direct proof. So here we go. If you turn left at A, then you can get to point B. All right. If we follow the syllogism approach, we're going to take the conclusion of that first one and make it the hypothesis of the next one. So we'll start out, if we can get to B, then you can get to C. Maybe you see where we're going with this then? If you can get to point C, then you can get to point D. And finally, if you can get to point D, then you have completed the maze. So in other words, we started with if you turn left at A, and we ended up with then you have completed the maze, which, if you'll notice, is up at the top there, isn't it? That's the theorem that we were trying to prove. Now watch how we got there. A implied B, B implied C. These are all facts, things we can see from the maze. C implied D, D implied E. Therefore, A, if you turn left, implies E. That's direct proof. We've proven that theorem up above. If you turn left at A, then you can complete the maze. It's a direct proof. In symbols, it would look like this. If A is true, then B is true, and so on all the way down. Therefore, and you notice the 3 dots, that's an abbreviation for therefore when we're doing logic. Therefore, if A is true, then E has to be true. That's a direct proof. We can shorten it up just a little bit. A implies B, or if A is true, B is true. It means the same thing, it's just a little bit shorter way to write these out. That's direct proof, using facts to prove other facts to end up with a new theorem. Direct proof. Let's go back to this maze and try to use an indirect proof. Indirect proof. How's that going to work? If we're trying to prove that you can complete the maze, when you use an indirect proof, we're going to suppose the opposite of that. We think you can complete it if you go left. But let's just say if you go left, you can't complete it. All right, now we're into syllogism again. If you can't complete the maze by turning left at A, then we must go straight. Well, that's what it looks like down here. If we can't go left, the only other option is to go straight. But if you go straight at A, then you cannot complete the maze. It's pretty clear from the picture. That's a contradiction. We just can't get to completing the maze by going straight ahead. Therefore, and this is the phraseology you have to get in your head, therefore, what we supposed was false, that you can't complete the maze. And if you turn left at A, then you can complete the maze, which is the theorem we were trying to prove. Okay, I'm going to back up and just take another quick look at that without interrupting. Suppose you turn left at A and you cannot complete the maze. We're trying to prove that indirectly, so we suppose the opposite. If you cannot complete the maze, you must turn, by turning left at A, then you must go straight. But if you go straight at A, you cannot complete the maze, which is a contradiction. Therefore, what we supposed was false. And if you turn left at A, then you can complete the maze. So we use two different ways to get to the proving that theorem, that if you turn left at A, you can complete the maze. Here's what it looks like in symbols. If we're trying to prove if A, then E, we say, suppose not E. Okay, well, if not E, then F. If F, then G. But G is a contradiction. So what we supposed is false, up here, not E. And if A, then E, what we're trying to prove up here. So you're trying to prove it, suppose the opposite, run into a contradiction. That means you proved what you were trying to prove. In our anno hat trick, there were 3 of them. This is the one we're going to take a little look at here indirectly. This is the thinking that should have been involved. So the theorem is we think our hat is pink. Well, let's just suppose the opposite of that. So we work indirectly. Let's suppose our hat is not pink. Okay, fine. We can do that. If our hat is not pink, then it is green. If our hat was green, then our classmate would know his hat is pink, since there's only one green hat. But our classmate doesn't know what color his hat is. This contradicts the fact that our classmate doesn't know the color of his hat. Therefore, what we supposed, we're looking way up here, what we supposed our hat is not pink, that's false. And our hat is pink, which is what we were trying to prove. We think our hat is pink. So we've used an indirect approach to proving our theorem. Looking at the 2 types of proof side by side, here we see on the left side a direct proof. We use facts we know, and only that. Follow the syllogism approach. Prove that if one thing is true is the next, therefore what we started with and what we end with are true. In an indirect proof, you start by supposing the opposite of what you're trying to prove. If we're trying to prove then D, suppose not D. And then follow along with the syllogism approach. Keep going on and on until you reach a contradiction. Therefore, not D is false, and D must be true, which is what we were trying to get to. These get a little confusing, so you need to practice with them. The author does a good job of walking you through them in Lesson 4, the problem sets. Starts very basically with something that is so silly it gets confusing. So Sam Goldwyn, maybe you've heard of Goldwyn Mayer, GM Productions. He says, I'll tell you what I think in 2 words. Impossible. Obviously it's 1 word, but the way he says it makes it sound like 2 words. This statement describes what is eventually reached in a certain kind of proof. What is it that is reached in a certain kind of proof in 1 word? Well, did you get that? You run into a contradiction. According to the way that Goldwyn would say it, name this kind of proof in 2 words. That's in quotes. Kind of like 2 words up here. Impossible. What kind of a proof sounds like 2 words? All right, so here we go. This first one is just getting you started on indirect proofs. If you're going to prove a theorem indirectly, you begin by assuming the opposite of the conclusion. So list the assumption you'd use to start an indirect proof. Here's an example. We're trying to prove that if a tailor wants to make a coat last, he makes the pants first. All right, well, indirectly, if we're trying to prove he makes the pants first, let's suppose the opposite. Suppose he does not make the pants first. And that's as far as he takes you with these first couple. So look them through. Try to get a start to an indirect proof. I had this one on one of those daily calendars one time, showing how things aren't always as logical as people like to think they are. Canton, Mississippi. The city council decided this: to build a new jail. Got it. To build it out of the materials of the old jail. That makes sense. You might as well save some money. And then just go ahead and use the old jail until the new jail is finished. Do you right away see the problem where he's going with this? Yeah. So now they want to know, are there contradictions with some of these? Conflicts. In other words, could A and B both work? Could B and C both work? Could A and C both work? One of those sets, at least one, has a conflict or a contradiction, which is what we're trying to look for. It just couldn't happen. We have a Keith Devlin up here, mathematician and an author. And here's what he said. As so often happens in mathematics, the best bet is to look for a proof by contradiction. That word should make you think indirect proof. Once you have obtained your contradiction, you will have achieved your goal. Since contradictory conclusions can be obtained only from false assumptions. So the idea is, in our proofs, we assume the opposite of what we're trying to prove. We prove that, by contradiction, that it was false assumption, which means what we want to prove is true. So now he just asks you two questions here. What kind of proof is that? And how is the assumption that he's talking about here, that is proof false, how is that related to the theorem that you're actually trying to prove? All right, next one. Another approach at a person using indirect proof. And I think you guys actually use these at times without realizing it. You say something like, blah, 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 blah. Yeah, but he didn't do that, so it can't be that way. So maybe the yeah, but is the thing that gives you a hint as to an indirect proof. Well, here's an example. 13th century, he's talking about the shape of the earth, and here's what the author says. If the earth were flat, the stars would rise at the same time for everyone, which they do not. So let's just, I always encourage this, look through this and think about it first before you get to the questions. Can you tell from this whether you think the author thinks the earth is flat or not? If the earth were flat, the stars would rise at the same time, which makes sense for everyone. If it were just a flat plane out there and up comes a star, everybody would see it. Then he goes on, which they do not. And that's true. Depending on where you are on the globe, you will see different stars at different times. So now the question, what is the author trying to prove? With what assumption does he begin? Where do you see a contradiction? And what does the contradiction prove about his beginning assumption, this number 12? What does the contradiction do to that? Okay, set 3. We've got 3 or 4 different situations here where a problem is posed and you have to think it through indirectly. And they've left out a step, so you have to figure it out. You have to fill it in. We did this earlier with direct proof. So here's the setup. You need to read that paragraph up there. A classroom has 5 rows of 5 desks, so you got 25 desks there. The teacher asked the pupils to change their seats by moving either one seat forward or back, or one seat to the left or right. That seems pretty straightforward, pretty easy to do. You say, well, yeah, but if you're in the front row, you can't go forward. No, but you could go backward. Or you could go left. If you're in the back, you could go forward. I guess I said left. That would have been right, wouldn't it? If you were in the back, you could go forward or you could go left. So seems like a pretty legit rule. So they work through an indirect proof trying to determine, is that true? We think they can't obey the teacher. So how are you going to begin? What assumption are you going to use? If we're trying to prove they can't obey, we're going to start by saying what? The next line here kind of gives you the hint, doesn't it? Because we're using logical deductive reasoning. And remember what you do? You take the conclusion of the first statement and make it the hypothesis of the second one. So that kind of gives you a hint, doesn't it? If they can obey the teacher, the 13 pupils in the black desks will move to the brown desks. Look at the figure and tell what the contradiction is. And then finish the indirect proof. Therefore, our assumption, whatever you had right here, is false. And what conclusion has to follow? Well, it's whatever your theorem is trying to prove. Another example of that here, again, pay attention to the directions. We've got 3 hydrogen atoms bonded to a nitrogen atom, as in that picture. And one given that we have is that the bond angle is 107, 107, 107, 107 between the bonds. And so we're going to indirectly prove something here. We're going to prove that the atoms are not coplanar. In other words, these 3 don't lie in the same plane. Well, if you're going to do it indirectly, how do you start? It's an indirect proof, so if you're trying to prove that they're not coplanar, how would you start? And again, they kind of give you a hint here by the next step. Follow through the logic. If the atoms are coplanar, then the sum of the 3 bond angles is 360 degrees, 1, 2, and 3. If the sum of the 3 bond angles is 360, then each angle would have to be 120 because they're the same, 360 divided by 120. What does this contradict? And again, how do you end indirect proof? Therefore, our assumption is false, this assumption right here, and what conclusion must follow? Hope you're just pausing here when you need to. Poker proof. Okay, you know what what is it called? A royal flush. That's what I'm looking for. You know what a royal flush is? When you have 10, jack, queen, king, and ace of the same suit. Okay, so here we're using indirect reasoning, and I think it's pretty obvious. This is the hand that you have. There are no wild cards, and you've been dealt 4 of a kind, all 4 tens. Our theorem is, we're pretty sure, in this deal of the cards, no one holds a royal flush. And you say, well, duh, that's obvious. Well, here's where the indirect reasoning comes in. It happens really quickly in your head. You already did it. If you know the answer, you already did the indirect proof without even thinking about it. How so? Well, how would you begin if you're trying to prove no one has a royal flush? You'd say, what? Well, and again, if someone holds a royal flush, then one of the 10 cards would be in his or her hand. What does this contradict? Therefore, our assumption is false, this line, and what conclusion has to follow? Again, as I said, you probably did that one in your head in about 2 seconds. Here's another puzzle, puzzle 1 and puzzle 2, using indirect proof again. In each case, the puzzle is to separate the weights into 2 sets so that one set will exactly equal the other. So divide this one into 2 sets so that one set equals the other. Same down here. Can you solve either puzzle with that set of conditions? So they walk it through here, step by step, what conclusion follows. Consider this argument. And again, there's some missing steps. And again, get used to this. Therefore, our assumption is false, and what conclusion has to follow? Clever Athletes puzzle makes you think a little bit, and in the process, you're going to be using some indirect reasoning in your noggin, hopefully. Are you as smart as you think? At a sports banquet, there are 100 famous athletes. That's a given, 100 people. Each one is either a football or a basketball player. So, 50-50, 60-40, 90-10, 99-100, what is it? So each one is either a football or a basketball player. At least one is a football player. Given any 2 athletes, so out of the 100, grab any 2. At least one is a basketball player. So again, think that through a bit. At least one is a football player. And if you take any 2 of them, at least one is a basketball player. The question, pretty straightforward. How many of the athletes are football players and how many are basketball players? But for the next point, you need to explain your reasoning there. Explain how you get there. Make it indirect proof. Well, it's going to be, but try to get it written out in a way that shows you understand you're doing it indirectly. And then finally, set 3. Oh, look at that. I was practicing early, and it looks like I didn't get everything erased. All right. So here's a puzzle, D.L. Silverman, to decide which of the following statements must be true and which false to avoid any contradictions. So here are our statements. Some are false, some are true. Exactly one statement on this list is false. Could that be true, or is that false? Exactly 2 statements on this list are false. Exactly 3 statements on this list are false. Exactly 4 statements on this list are false. So now he asks some questions to try to walk you through this. Really what we're trying to get to, tell me which statements are true, which are false. So hopefully you get this worked through ahead of time so you can come to class with any questions. This is one of the more confusing we've had so far. Good luck with that, and be ready to ask whatever questions you need to ask in class. All right.